Hi everybody, today we are going to talk about linear function patterns. So a linear function is any function that you can write in the form of y equals mx plus b, which should look very familiar. This is our slope-intercept form. So I want to show you guys some examples of linear functions and then some non-examples so you can know what to look for. So like y equals x, y equals negative 2x plus 4, y equals 2 over 3x minus 2. Anywhere where you can easily see the slope and the y-intercept. Even y equals 1. This is just a linear function with a slope of 0. Now compare that to our non-examples. If you have y equals x squared, square root of x, 1 over x, or just an x and no y, these are all not linear functions. So if you try to generalize and say, hey, what makes a linear function or what doesn't make a linear function, essentially anytime you see something other than just x. So x squared, square root of x, 1 over x, and then anytime that you don't have a y as well, it will not be a linear function. But of course, we can always think back to our more formal definition. It can be written in the form of y equals mx plus b. So if we are told that something is a linear function, it means that it's going to follow certain patterns that all linear functions follow. So first of all, if we know that something is linear, we know that we can use any of these formulas to help us define the function. So these are all formulas we've used before. We have our slope formula, which is y2 minus y1 over x2 minus x1, which is also rise over run. Is another way we described it, or we could say change in y over change in x. So this is how we find the slope of a linear function, but it only works for linear functions. Now we also know slope-intercept form, y equals mx plus b. If we know it's a linear function, we can use this formula. And we also know point-slope form, y minus y1 equals m times x minus x1. So you'll notice that one thing that all three of these have in common is slope. So finding the slope is the most essential part of defining a linear function. Now these two, the only thing that's different for these two is the point that you have. So if you have the y-intercept, which is a very specific point, we can use y equals mx plus b. But if you're not given the y-intercept, you can use any point, any coordinate on the graph, which is x1, y1, and you can make the equation the same. So the only thing that's different between these two is here you need a specific point, here you can use any point. So let's see if we can look at this graph, which we're told is a linear function, and let's see if we can write an equation that relates y to x. So we are just going to use y equals mx plus b. So we're going to use our slope-intercept form to make this function. So first, of course, we need to find our slope. Now we can do this in two different ways. One, we could use our slope formula, which is y2 minus y1 over x2 minus x1. So I can pick any 2 points on the graph. So let's say I pick the points 2, 0, and 4, 3. And I can label it x1, y1, x2, y2, and I can do my little substitution. So m equals y2 minus y1 over x2 minus x1. So my slope is 3 over 2. But of course, we know that we can also tell the slope just by looking at the graph. So we can pick any 2 points, and we can actually do rise over run. So here I see that my rise is 3, and my run is 2, giving us the same slope. So our change in y is 3, change in x is 2. So either way, our slope is the same. So now we have our slope. So our slope, our m value, is 3 over 2, but we still need to find our b value. So here we can tell that by looking at the graph. So our b value is going to be our y-intercept, which is where our graph crosses our y-axis. So it crosses right here. You can also tell a y-intercept because it occurs when x is equal to 0. So I can see that our b value is going to be negative 3. And now we can just plug it into y equals mx plus b, and we get y equals 3 over 2x minus 3. So however you want to do it is fine, whether you just want to look at the graph to find the slope or you want to use the slope formula using any 2 points that you choose. Either way, you should get the same result. Now we're going to do the same thing, except we're going to use a different representation of data. So it just looks a little different. Instead of a graph with points plotted, we're given an XY table of values. So they once again tell us that it is a linear function. So we're always going to start by finding the slope. So for this one, a few different ways we can do it as well. Let's do change in y over change in x. So remember, to do that, we just pick any two y values and we see what's the change from one to the other, and then we match it with our x values. So from 9 to 7, that's a -2. And from -3 to -2, we're actually adding 1. So my change in y is -2, my change in x is 1, so my slope is -2. Now you can use any 2 points you want, you'll get the same answer. For example, if I chose to go from here to here and I match it on top, from 7 to 4, from 7 to 3 is subtracting 4, and from -2 to 0, I'm adding 2. So if I do change of y over change of x here, we get -4 over 2, which is also -2. So it doesn't matter how you find or which values you use for change in y over change in x, as long as the change in y is in the numerator and the change of x is in the denominator. Now, of course, we also need to find our b value. So remember, our y-intercept occurs when x is 0, and I see that that's happening right here. So once again, we know it's the y-intercept because x is 0. So that means our b value is 3. So if we use y equals mx plus b, we have y equals -2x plus 3, and that's our linear function. Okay, why don't you go ahead and pause the video and give these two examples a try. We'll check our answers in just a minute. Okay, so for our first one, if we do our rise over run, you'll notice that we do have to go down to get to our next point, which means our slope is -1 over 2. And I can see here that my y-intercept is -1, so we have y equals -1/2 x minus 1. For the second example, if I do change of y over change in x, I see that my slope is actually 0. It's okay to have a 0 in your numerator, and it's okay to have a slope of 0. This is just a horizontal line. So my y-intercept I can still find is right here. So if I plug it into my slope-intercept form, y equals mx plus b, I'm left with just y equals 2. We don't leave the 0x. But remember, it's okay to have a slope of 0. All it is a horizontal line. Okay, so we're going to try one real-life application problem together so you can see why it's actually useful to be able to create a linear function. So first they give us this example, this data. So this data represents the number of calories you burn for each hour that you spend kayaking. So you can see that our x-axis represents the number of hours and the y-axis represents the number of calories burned. So the first thing they ask is this domain discrete or continuous? So I want to remind you guys, a discrete domain is when it's only certain points and then there's gaps in between your points. Continuous is when it can be any value along the way. So since we see that the line is connecting through the dots, we know that this is actually a continuous domain. And remember, domain is just all of the x values that work. Now, another way you can think about it is if you see what our x values represent, it represents the number of hours. And it's possible to have 1 hour or 2 or 4, but it's also possible to have 1.5 hours or 2.25 hours. It's possible to represent time in smaller increments. So that's how we know that it's a continuous domain. Now they would like us to write a linear function that represents y to x. So for part B, so this was part A, for part B, let's see if we can use y equals mx plus b again. So let's start with the easy one. Let's start with our b value. So I can see this graph actually hits at the origin. So I know that b is 0. And now let's find our slope. Let's find rise over run. Here, you just have to be careful about the units on your y-axis. you can see that I'm not actually counting by ones. In this case, one box means 300. So my rise, I know it looks like it's 2, but my rise is actually 600. And my run is 2. For my x values, each box represents 1. So if I do rise over run, my rise again was 600, my run was 2, so my slope is 300. So the equation that I have is y equals 300x, and I don't need to say plus 0. So this is the function that will tell me the number of calories I burned for how many hours I kayak. So the number of hours is the input, and the output is the number of calories I burned. So this is useful because we can use this function to help us find how many calories we burn for any amount of time. We pick the amount of time, you plug it into x, and we can find y. So for part C, you can see that they're asking us to find how many calories do you burn in 4.5 hours. So essentially here, they're just telling us that x equals 4.5. And I can plug it into our function. I'll substitute it for x. And that will tell me the number of calories I've burned. So let's do our little multiplication on the side. Okay, and then for my decimal point, it's been moved once in my problem, so I move it one time in my answer. So we get y equals 1,350. So of course this is a word problem, so we want to answer it thoroughly. So let's say in 4.5 hours, you burn 1,350 calories. So if you're able to make a function like this that defines a set of data, we can find any y value for whatever x value we pick. So like what if we wanted to find how many calories you would burn if you kayaked for 100 hours? Instead of having to continue your graph or add everything up, we just plug in x equals 100. So being able to describe a real life situation with a linear function is actually really useful. All right, that is all for today's lesson. Thank you so much for watching.